All right, guys, sound good if we start off the video? Just for logistics stuff, we're going to do like 20 minutes of the keynote, just kind of the more interesting technical stuff that Jonathan went over in the keynote. A couple people were there, but hopefully you forgot some of it. You can watch this online. I'm just streaming it from YouTube, but I know if you're anything like me, I'll bookmark something and then never ever watch it, so I figured it would be a good chance to show some of it at the meetup. We'll do that. We'll take do a little Q&A after that if anybody has any questions. And then Tyler's going to do run through a presentation that was also given at the summit by another guy that works at Stack named Carl. And that presentation's on materialized views, so some of the in-depth things there. So that should be good. Somewhere in the middle there, I actually have to take off, and so when that happens, I will be taking the beer and the pizza and the swag with me. So within the next 30 to 40 minutes, if you want to get all of that you will possibly want, because after I leave, it's gone. For November, we're having a November meetup. I'm not quite positive what it is, but I'm hoping to figure it out next week sometime. It might be another summit presentation that a DataStax guy did, and we'll have him do that here, or it might be a presentation from a local Austin company that I'm still trying to figure out. So should be a good one. I'll try and get it email out soon so you guys can get it on your calendars. If you want to give a presentation or have any topics you want to hear about, oh, hi Steve. Let me know. Yeah. Otherwise, I'll get started. So I guess just background on the keynote. This is, an hour and 6 minutes into the keynote. It was a 2-hour keynote, so it's quite a long one. The beginning started off with kind of a presentation with setting Raspberry Pis on fire and smashing them, which was kind of cool. So I recommend going back and watching that if you want to. And then there was quite a bit by Billy Bosworth, our CEO, and he also brought up Scott Guthrie, the VP of Cloud at Microsoft, and they did some stuff. But this part is Jonathan Ellis, chairman of Apache Cassandra project, talking. He's actually already at this point talked a little bit about very, very high level Cassandra, what it's good at, and things like that, which I assume most people here already have a pretty good grasp on. So he skipped over that, and now he's talking about the recent Cassandra 2.2 release, the upcoming 3.0 release, which is in alpha, and then going forward for the future. So get some good info there. Alrighty.
So now that you understand what Cassandra is designing for around performance and around scale and around availability, I want to talk about what we've been working on in Apache Cassandra 2.2 and 3.0 to make Cassandra even better at these characteristics. Now, a year ago at the summit, I talked about Cassandra 2.1, and at the time, we were planning to go from 2.1 straight to 3.0 and deliver a traditional big release full of features in 3.0. What we found was that we were introducing a new storage engine in 3.0, but not all of the features that we were planning depended on that storage engine. In fact, most of them didn't. So we split it up into 2 releases, and we said we're going to try to get people the new features as fast as possible. So we're going to split out those features that don't depend on the new engine into 2.2. And then the features that do depend on the new engine, those are going to be in 3.0 a little bit later. So 3.0 is in release candidate now. We released that on Monday. We expect it to be generally available in October. 2.2 was released back in July. So that's everything here is available for you to test and play with. So the first feature I want to talk about in 2.2 is JSON support. Now, you know that Cassandra thinks about the world in terms of rows and columns, and I can have a table that looks like this, and I can insert data into it with a SQL statement like this. Starting with 2.2, I can do all of this in JSON as well. So the syntax for that says insert into table name JSON, and then I give it a JSON document literal, and Cassandra will parse that and transform it into its native representation. This is designed to allow Cassandra to seamlessly integrate into a world of JSON-based microservices. So there's actually a subtle difference in the two statements that I gave here. And you'll notice that in the CQL statement, I generate my user ID with the built-in function now that creates a time-based UUID. Whereas in the JSON example, I'm giving it a UUID literal. And that's deliberate because in the JSON world, the idea is I'm consuming data from another service rather than generating it myself. If I'm generating the data myself, it's probably a better idea to stick with CQL, but you do have that choice. CQL allows you to nest data structures in your Cassandra rows, and we can expose those to JSON as well. So we introduced collections back in Cassandra 1.2. Here's a table that has a tuple, a set, and a list column types here. And so I can insert into that table with CQL like this. And note that my tuple is represented with parentheses around the values, the set has curly braces, and the list has square brackets. So I have different representations of each of those literals in CQL. So in JSON, I only have a single kind of sequence literal. And so that's the list literal in the square brackets. And so if you give me a JSON value, and I know that under the hood in Cassandra, it's a tuple or a set, I can coerce that JSON list and transform it into the appropriate Cassandra type. The other way to nest data inside Cassandra is with user-defined types. And a simple user-defined type looks like this, where I have an address, a street number, and street name. And then I can use that in my table definition and say I have a street address column that is an address value. And then I can insert into that with CQL, and then with JSON as well. So a user-defined type becomes a subdocument in the JSON world. And we can take this further. We can nest things arbitrarily deeply in a Cassandra table and expose those to JSON. And the reason you'd want to do this is you want to denormalize the data that your application needs for a request into a single Cassandra row. So you're not having to join data from different machines together in a given request. Nesting data into a Cassandra table makes that easier. So let's take a slightly more complicated address definition where now I have a set of phone numbers associated with each address. And then I'm going to let users have multiple addresses. Now my users can have a home address and a work address, and we'll just let you supply any kind of address you want. You give me a text key and then an address value that it maps to. And so exposing that to JSON looks like this now, where I have the ID and the name literals at the top, and then the addresses collection becomes a subdocument, and my home address becomes another subdocument inside that. So again, what this does is it lets me build modern microservice-oriented architectures and play with those with Cassandra in a frictionless manner, and reducing the obstacles to being able to build those applications. We've also added in Cassandra 2.2, we've added Windows support. And I announced at the summit last year that 2.1 was kind of an extended beta for Windows. Now in 2.2, it's production ready. And as a first-class citizen, we expect it to be on a level playing field with our Linux support. We've also added support for role-based authorization. And what this is intended for is for larger enterprises that are managing multiple members of a team. We want to avoid the problem where, through human error, some members of the team have different permissions than the others. So you can create an accounting role, you can assign permissions to that role, and you can assign users to that permission, and Cassandra makes sure that that all stays in sync. So as you add users and remove users from your accounting team, all you need to do is add and unassign that role, and that possibility of a mismatched permissions goes away. We've also added user-defined functions. And the idea here is we want you to be able to push logic closer to the data in the Cassandra cluster. So as a very simple example, this is how you would define a sign function that computes the mathematical sign in Java in Cassandra. So you say, create function, you give it the parameter list, you give it the language name, and then you give it the function body. That's all there is to it. Out of the box, we support Java and we support JavaScript, but we support integrating with any JavaScripting API compatible language. So if you want to write functions in Ruby, just drop the JRuby jar in your class path, and you can create functions in Ruby and Cassandra. So I can invoke this function like this in my select statement, where I'm invoking the function on a column called value. And you may be thinking that this actually doesn't look terribly useful, because whether I compute the sign in the Cassandra cluster or whether I compute the sign in my application code, that doesn't really matter a great deal, because I'm pulling the same amount of data back to my application server either way. And you're right. So the more important thing that these user-defined functions enable is the ability to compute aggregates at the server side. And an aggregate's a little more complicated, because I need to define an intermediate state function that accumulates values that are being processed, and then I need to define a final function that gives me the final value from that intermediate state. So for my average function, I'm going to have an intermediate average state, and that looks like this. And all this is doing, this is saying that as values are fed in to my averaging function, I'm going to increment a count of values that I've aggregated, and I'm going to increase the running total by the value that I just saw. That's what this says. And then my final state function is going to take the running total and divide it by the count to get the final value. So now this is a lot more useful, because I can combine thousands of values at the server and compute the average without having to leave the server, and then I can just send the average that the client wanted back to him, and that's much more efficient now, much more efficient use of network resources. Finally, for 2.2, we added commit log compression. You'll remember that for 2.1, we did a lot of effort on our performance for CQL reads and writes, but we were starting to be bottlenecked by commit log performance and by the amount of data we could push to a single disk. And so we've alleviated that bottleneck in 2.2. So you can see in green, Cassandra 2.1 performance, 2.2 in blue is about 10% faster. But not only is it about 10% faster, but you can see that there are kind of spikes in the 2.1 graph where it has to pause briefly for the commit log to catch up. And those pauses have been eliminated in 2.2, so it's not only faster overall, but it gives you more consistent performance. Commit log compression is kind of experimental in 2.2. It's off by default, but it's going to be turned on by default in 3.0. And I encourage you to play with that. You can turn it on a single machine, make sure everything's still stable, and then roll it out to the rest of your cluster. Finally, date tier compaction strategy is a new compaction strategy that we created during the 2.2 timeframe, but it's not actually limited to 2.2. Because we designed compaction strategies to be pluggable, we were actually able to take this back to 2.1 and even 2.0 without risking the stability of the system. So I'm going to show you two graphs that illustrate date tier compaction performance. And what this is designed for is designed to handle dense time series workloads and allow you to pile a lot of data, even cold data, on a single box. So what I've done in this workload is I've actually pushed out all the way to 18 terabytes of data on a single machine. And so this graph here, this is the read performance. So I've put leveled compaction at the bottom, size tiered compaction in the middle, date tiered compaction at the top, and you can see how each of those compaction strategies compares across this data set. Leveled compaction, as you're probably not too surprised to find out, falls off a cliff at about 2.5 terabytes of data. And you're probably not surprised because leveled compaction is designed for read-mostly workloads. This one is 90% writes. So it's very write intensive. And you also see on this graph that on the reads, date tiered is outperforming size tiered. And you're probably not surprised by that either because size tiered is designed to give you better write performance. So let's look at the write side of this workload. And now that this is probably a little more surprising that even on writes, date tiered compaction is outperforming size tiered, because it can take advantage of what it knows about time series data to avoid unnecessary disk activity and wasting that I/O on data that doesn't need to be compacted together. So that's what's coming in 2.2. We have a lot of new features across the board. I mentioned earlier that we pulled out into 3.0, we pulled the new storage engine into there. And that touches everything in the system, and it enables new features that we couldn't do with our old engine. Our old engine, it served us well, but fundamentally at the atomic level, it thinks of data in key value pairs. And so to deliver features like materialized views, we needed an engine that understands SQL semantics at a more fundamental level. But even without those new features, there's one important benefit you get from the new storage engine, which is that it's much more space efficient. And how much more space efficient depends on your workload. And it depends dramatically. It can go from saving you 50% on one of these workloads to 70% on another. What I can give you as a rule of thumb is that data models with a large number of collating columns are going to save more space in 3.0 because that's one of the places where we're able to pull redundant information out and store it in just a single location. Another improvement we've made in 3.0 was around hinted handoffs. So I showed you earlier that in a Cassandra cluster, I can have any node route the request to any replica, and if something goes wrong, we don't need to panic. It's designed to handle that. One of the ways it's designed to handle that is with something called hinted handoff, where if any replica doesn't acknowledge an update for whatever reason, the coordinator will write what's called a hint to itself that says once that node comes back online, or I'm able to talk to him again, we'll send that missed update over. And delivering that hint is called handoff, so that's where the feature name comes from. The problem with hinted handoff has been that we've stored the hint data in a Cassandra system table. And so that looks like this, where when I write the hint, it goes first to the commit log, then we sort it in a mem table, and finally we write it to disk. And then when we delete the hint after we successfully deliver it, that deletion creates a tombstone in the commit log, in the mem table, and on disk again. And we're still not done, because right now in this picture, I have the original hint in one data file and the tombstone that says it's deleted in another. So I actually need to compact those together to reclaim that disk space. And so there's a lot of overhead in this design that doesn't actually help us in hint delivery, because we don't care about indexing hints by their ID or random access to different hints that Cassandra's storage engine is designed to provide. All we care about is store a hint safely and then bulk deliver them. So for 3.0, we created a very simple custom storage engine for hints. And it just looks like this, where I'm going to create a flat file for when a replica doesn't acknowledge my update, and I'll just append hints to that file, and I'll do that for every replica in the cluster that I need to store hints for. And then when the replica comes back online and I deliver those hints, I just delete the entire file at once. So it's very, very lightweight because it doesn't need the extra indexing that's going on in the main Cassandra storage engine. So the performance difference that you can get out of this, it varies widely based on your cluster size. So I have here the most extreme possible example where I have a 2-node cluster and one of the nodes is down and I'm writing hints for it to the other. And this is extreme because as my cluster size grows, the responsibility for storing hints for a dead node gets spread across all the nodes in a cluster. So in a 10-node cluster, you'd expect the difference to be about 10% as large. But in this extreme example, 3.0 is about twice as fast as 2.2 in this degraded situation. And this comes back to what I said earlier about how we want Cassandra to be able to scale down as well as scale up. And this is one of the features that is more meaningful to smaller Cassandra clusters, because those are important too. Finally, I said that the new Cassandra storage engine allows us to build materialized views for the first time. What that looks like is, suppose I'm collecting songs in my application, and each song has an album associated with it. And I want to ask Cassandra what songs belong to a given album. So with materialized views, I can create the view and say select star from songs, and my primary key now is going to be not just the ID, but first the album and then the ID. And by doing that tells Cassandra to partition the data by the album. And so now I can go and I can say select star from songs by album for a given album, and Cassandra can give me that song list. And you're probably thinking, this sounds a lot like indexes. And functionally, they're very similar. I can take my songs table, I can create an index on the album, and I can select from the table using that index. So it's functionally very similar. The difference is that indexes are managed locally. Each node in the cluster indexes the data that it owns. So what that means is when I go and I ask an index what songs are in this album, Cassandra has to scatter that query across the entire cluster. And then each node can look up in its local index, oh, do I have any songs in this album? And then we gather back those responses and feed them to the client. So as a consequence of this, if I go from my 6-node cluster here and I'm doing 10,000 requests per second, and I go up to a 60-node cluster, then I'm still going to be pushing around 10,000 nodes per second, because the bottleneck has become the scatter and the gather parts of the operation. By contrast, a materialized view, since Cassandra is repartitioning that data in your view, I only have to go to a single replica. I can go to the replica that owns the partition for the Tres Hombres album, and I can get all the songs back from that one replica. So now when I go from a 6-node cluster to a 60, then I expect my performance to go from 10,000 per second to 100,000. Now the read performance of a materialized view is absolutely identical to the read performance from a normal table. It's the exact same code path, managed the exact same way. But I want to give you some idea of what to expect from the write performance in your cluster as you introduce materialized views to it. So we're going to look at that a couple ways. The first way is to, let's take the writing to a table without any materialized views at the top here in purple, and then in the red line I have a single materialized view that I've added, and then in the purple at the bottom I've got 5 materialized views. So the rule of thumb is that adding a materialized view to your table will cost about 10% of your performance. And this is done just with the standard Cassandra stress tool. But we also wanted to look at this a slightly different way and say, given that I need to denormalize this data for my application, I either need to do that the old-fashioned way by batching up those updates to tables that I'm maintaining by hand in my application code, or I can have Cassandra do that with a materialized view. So to compare those two approaches, we created a custom benchmark tool called MVBench, and this is what our performance looks like for 4 materialized views against a base table of playlist data. So the materialized views are delivering 50 to 80% better performance than doing it manually, which is good because not only is it more convenient, by pushing that logic to the server, I can deliver very better performance. But you'll notice one thing with this materialized view line, which is that it looks like it's trending downwards over time. And that's not an accident of the benchmark. That's actually caused by something real going on under the hood. And what's happening here is that in my base table of playlists here, as I'm inserting more and more data into each of those playlists, I'm increasing the time I spend in lock contention against the base table. Because materialized view maintenance needs to take out exclusive locks against the base table to keep the views consistent with the base table data. And so as a rule of thumb, that contention starts to become meaningful at about 200 rows per partition. Fortunately, most tables that you'd want to denormalize with materialized views have small partitions. But this is something that you're going to want to keep in mind as you incorporate materialized views into your data model. So we've talked about what's here in 2.2, what's coming up in 3.0. I want to take just a couple minutes to talk about what's coming after 3.0. And in particular, what we're doing to make Cassandra delivering features to you on a more regular basis and with even better stability. And so you saw a little bit of our telegraphed approach when we split 2.2 off of 3.0, because smaller releases ship faster and they're more stable. And so we want to go even farther. We're going to start doing monthly Cassandra releases to give you more features and better stability. And we didn't just want to jump to doing monthly releases because that would be a good way to let our feature development get ahead of us and cause problems. So we looked to Intel's TikTok development process for inspiration. And what Intel does is they split their microprocessor development into a tick of smaller transistors and new manufacturing process, and a talk of a new microarchitecture. And so by splitting those up, they reduce the possibilities for error and the possibilities for conflicts, and you get a more reliable schedule. So the way we're applying that to Cassandra is that every other monthly release will be a pause in feature development and just include bug fixes. So 3.0 we expect in late October. We'll begin the TikTok releases at the beginning of December with 3.1, which will be just bug fixes. Then 3.2 in January will include new features. 3.3 will be just bug fixes, and so forth. Now, if you're paying attention to the industry recently, Intel has actually had some hiccups in their TikTok process. And we're realistic enough to acknowledge that we'll probably have some hiccups as we move to this development process as well. So what we're doing is, in parallel with the TikTok process, we're going to continue to deliver traditional stabilization releases of the 3.0 line. So we'll release 3.0.1, 3.0.2, and so forth, and each of those will not include any new features at all, but strictly contain bug fixes. The other thing that people ask me about when I describe the TikTok's process is, well, what about compatibility? And the answer is that we're going to be 100% compatible across the entire 3.x TikTok line. And at some point, probably in about a year, we'll introduce 4.x, and that will be our line at which we sunset deprecated features and so forth. But for that entire 3.x series, it's going to be 100% compatible. I hope you're as excited as I am about the new features in Cassandra 2.2, what's coming in 3.0, and the new development process that will allow us to continue delivering new features at a regular cadence and keep Cassandra the best operational database in the industry for years to come. This is important.
Thank you, Jonathan.
Cool. So we can do some Q&A if anybody has questions and answers. If your questions are on materialized views, you probably should just wait until Tyler gets his talk.
Yeah.
But yeah.
But if you have any questions on, let's see, what else did he talk about? JSON, user-defined functions, aggregates.
Strategy.
Yeah, data compaction, new storage engine, new hints, TikTok, any of that stuff.
Is JSON already out?
Yes. Yeah, it's in 2.2.
What did he say Ruby would run on?
So that's if you drop the JRuby jar into Cassandra list directory. Yeah, it's anything that supports JSR 223. Yeah, so the only one I personally tested was Python, and that worked pretty well. I think I remember JRuby having some kind of issues. Hopefully they're fixed at this point, but JavaScript and Java work out of the box without adding anything else. And probably you get the best performance out of Java, so we expect most people to use Java in that case.
Is there Scala in the ecosystem?
I don't think Scala actually supports the scripting API. I'm not sure. Maybe they do.
I was going to say, I would imagine it would work, but...
Yeah, I don't think it would,
would.
but it might not.
I would guess if it doesn't work right now, it won't be too far behind given all our Spark work and things like that. Scala's probably going to be pretty high on the list.
That's true. That's true.
Do you guys work in Scala here in Austin?
No, but like since Spark is written in Scala and most people interact with it with Scala, and Spark is kind of becoming the de facto way to do analytics on Cassandra, I would imagine that we would prioritize Scala support for EDFs.
Well,
That's why I asked.
yeah, the language itself has to do some things like provide that scripting engine. So I don't
True.
know if it's something that we
Yeah.
can do ourselves. But
I mean, yeah, we're not Scala developers, so if it's anything too involved.
Wait, why would it have to go through the scripting engine API?
that's just the way that we implemented the user-defined functions for scripting languages. So we do something a little bit different for Java. We use, and what is the name of that? Something to essentially just, you can compile Java to bytecode and load it into a class that you can then execute immediately. So for Java, we actually compile it and just run the compiled version. But for the scripting versions, it has to do the whole scripting engine business. So
That's so, I mean, we don't want to tie ourselves to a specific version of JavaScript or Python or
right.
anything like that. So.
Have you heard any limitations about using that? I mean, do they recommend small functions that don't run for very long, I guess? But
Does it block the write path? Or, the read path?
No, it would just add a little bit of latency and extra CPU consumption on the write path or read path, wherever you're using.
Yeah, it's probably just, whatever your application can accept, you can
get out of it.
They don't OOM your server, but I don't know. There's a little bit of sandboxing around it, right?
Yeah, there is some
Probably not
sandboxing. I wasn't too involved in that part of it, but yeah, I think it restricts what classes you can access. I think there's some constraints on how long a function can run for. I don't remember off the top of my head. I don't know if that's something that's planned or if it's implemented yet, but I think we do want to put some kind of limitation on how long a function can run for to prevent an infinite loop or whatever. The aggregated functions, those use the built-in paging, so you don't have to worry about running an aggregation function over an entire table at once if you want to.
I thought it was limited to a partition.
No.
No.
I don't think so.
Will DSE start adopting a more aggressive release schedule along with the Cassandra release schedule?
Probably not. So, yeah.
I'm not sure. Yeah.
Neither of us are on the DSE team, so we can't be positive. But I don't think so.
Yeah.
Because they're always going for stability over features. So.
Right. I think they are planning to try to pull in 3.0 fairly quickly. So that's going to be a little bit more aggressive, but I don't know about after that.
Cool.
Anything else?
Let's see if your laptop actually works.
Yeah, let's find out.
That's a novel concept.
Got a laptop. The meeting works. So unfortunately, I do have to. I don't know if any of y'all were here for my talk a couple months ago, where I denounced PowerPoint slides and did something completely different. But I borrowed somebody else's talk, and unfortunately, guess what? It's done with PowerPoint slides. So it might not be my finest presentation yet, but it should be pretty good.
Speaking of that, I meant to mention earlier, but these are always usually recorded by Capital Factory, and eventually the videos make it up on YouTube. The talk he's talking about was a talk on the Cassandra internals right path or read path?
Read in right path.
Read in right path. And that made it up a couple of weeks ago, so that's up on YouTube. I posted a link to it in the comments of the meetup page that it was for, but you can always send me an email if you're looking for any of those videos. Those are always good.
You might want to put it on the about for the meetup group, a link to a list of them or something.
I'll have to look and see if, because it's through Capital Factory, so it's like there's a list of all the videos I've ever done, but they're not all Cassandra specific, so I'll have to see if I can.
Yeah, but you can just pull the Cassandra ones and instead of sticking it into the actual meeting, stick it into the about of the group,
Right.
so that you have, because who cares how long that list is?
Well, yeah, I just don't know how to get a list of only the Cassandra ones.
Well, if you pulled one, whatever you pull, I'm saying, I'm not saying.
Oh, sure, yeah, and just
Yeah.
update the list of links.
Right, instead of sticking it, burying it inside the event, which if someone comes along and they want to try and find it, they've got to go, what event was that? Excuse me, what event was that?
No,
You go
that's
into the
good.
about or top level.
Yeah, I'll look into that.
Was it the 3.0 preview?
That was a long time. So that's actually funny. If you guys were here back in March, Jonathan did a 3.0 preview then. That video's up as well, I think. 3.0 is still not out, even though he did the preview in March. But no, the one Tyler did is just called Cassandra Internals.
Don't watch the video while he's doing a new presentation.
I'm just trying to find it.
Okay. Cool. It works.
Last call for pizza and mugs. There's one mug left. Shirts and stuff. And one mug.
Well, I sold $2, so if someone wants one, I'll give it out. Take one for someone to work.
I think all the meat has gone.
Veggie's excellent. I recommend it. Got this. I'll wait for y'all to get it.
You've got underground drones.
Do what?
You've got underground drones.
Yeah, this is. So I have to put a big disclaimer on all these slides. I didn't make them. They're not my style. I tried to clean them up a little bit, but this was like an image that a lot of people used for the summit presentation.
Yeah, I was just saying, the standard summit.
Yeah. I don't really know. I don't understand it. Some marketers made it. It's not supposed to make sense. It just looks
I guess it
good.
was the Internet of Things was supposed to be big.
Right.
The two.
Right. All right. Let's move on to more meaningful things. Yeah. So actually, I forgot to say this was originally Carl Degsigian's presentation. So he does get some credit for having made these slides, I suppose. But I'm copying it. So Jonathan talked about materialized views a pretty good amount in the keynote, but the main reason I wanted to talk about them is because I think they're going to be one of the most important features in Cassandra in a long time and for a long time to come. Materialized views is basically what we tell everybody to do with their data model. It creates allows you to create multiple copies of your data that are laid out in ways that are amenable to the different ways that you need to query them. And the nice thing is that Cassandra is doing all the work here for you instead of it being very tedious for you to do it all by hand in your application. The thing that we really wanted here, and that is a big problem with the existing secondary indexes, is that you need good read performance, right? So materialized views have exactly the same read performance that you normally get. And like Jonathan mentioned, there is a bit of a write penalty, and I'll talk about exactly what that entails. So if you've seen my data modeling talks before, you know that the best way to set up your data model with Cassandra is to think about what queries you need to be able to support, and then you go through this denormalization process where you write out the same data, usually multiple times, to different tables that have different primary keys, and so that the data is partitioned differently or sorted differently on disk. And so it's optimized for how you want to query the data. And normally this means you have to make a different table for each query. You have to write the same code over and over again. And so something that's, Cassandra's always been kind of, it's been kind of a pain point, right? Your application code has to be a lot more complex because Cassandra can't do a lot of this stuff server side. So you need to handle a lot of this logic. And a lot of that is kind of tricky to get right in your application. A lot of people can miss some subtle problems around consistency between, say, the base table and a view. And they can also require locking to handle properly, read before writes, all that good stuff. And so it's pretty easy to mess up a few of these issues when you're doing it in the application. On the materialized views ticket for Cassandra, there's a lot of discussion just between Cassandra developers about exactly the right way to handle all these edge cases. And it's pretty much guaranteed that in your application, you might miss some of these finer details that even we had trouble figuring out how to deal with. So I'm going to use Carl's example here. It's kind of the same thing that Jonathan talked about, to just talk about materialized views a little bit. Say we're doing like a Spotify application. We need to support 3 queries. What songs are in a playlist, what artists end up in playlists, or how many playlists that a given artist is in, and the most recently played song for a user. So this is just an example of the tables you might have for your playlists. And if you're writing this in the application, you want to get all the songs in a playlist. It's just a pretty straightforward select. If you want to count how many times an artist shows up in a playlist, that's a fairly simple select count query. And similarly, to get the last or most recently played song, there's another query that you can run. But the main point is that of those 3 queries, only the first one is reasonably efficient. The last 2 are really expensive. And so this is where you want to start looking at, normally in your application, setting up a separate table that's optimized for handling that query. Let's see. So yeah, just like as an example of how you would set up a table yourself to keep track of the most recently played song, you set it up with the clustering order by last played descending. So then you can just pull the first row out of a partition, and it's really efficient. So this is just like the manual example of how you tend to do the denormalization. So really, if you want to do the manual version correctly, you need to do it with the batch statement. So the main thing that's important here is that this goes through the batch log. So I talked about this a little bit in my last talk, but the batch log is a way to help avoid partial updates whenever the coordinator fails mid-batch, right? So if the coordinator issues the first write out of these and then dies before it issues the second, or second and third writes, you can end up with partial updates. So the batch log records the entire batch on a couple of different replicas, and it continues to replay them. Come on. Thanks for pointing that out.
Yeah.
So the batch logs stores the entire batch on a couple of different nodes and essentially replays it until the entire batch has been successfully written. Deletes and updates are hard. I'm not exactly sure why he put all of these in here. Normally whenever you're doing this manually, there's a few steps. You have to do a lot of times a read before write to figure out what your existing version of the data is. So that's one trip to the coordinator. You read the base table, you get it back, and then you can figure out what you actually need to write for the new values. And if you go through that batch process that I just talked about, it has to go out and write to the batch log, and then it can actually proceed and write to the actual tables. So there's quite a few hops in this, and it actually starts to get somewhat expensive, illustrated by that. Let's see here, I meant to skip this. There are also problems around keeping the base replicas in sync with the views when you're doing this manually, right? So, say you, if you only have one copy of a particular piece of data in your base table, if you lose that replica, you may not know what values actually exist in the view. So you have trouble keeping the view up to date at that point. You don't know what the old existing value in the view is, so you can't properly delete it. And if you don't use any sort of a locking mechanism in your application or something like Zookeeper, it's really easy to do simultaneous updates that results in multiple entries in your view. There's an example of that in a little bit here. So, yeah, for example, on this most recently played, right? If two clients go and read the existing value, they can both go back, or they can both issue a delete to get rid of the existing previous value, but then at the same time, they'll both simultaneously update the view with what they think the newest value is supposed to be. And so at that point, you have multiple. Sorry, I was trying to figure out what I was going to say there. So, anyways, you can end up with multiple entries in the view, one of which is it's not the actual correct value, and you have no way of really knowing if this extra view entry exists. So these are all kind of the problems that you can run into with manual denormalization. Yes?
Are those clients locking in this case? Like where they do a read, they lock, and then they...
This is without locking.
Without
yeah,
locking. Okay.
Yeah.
Okay.
So if you don't do any sort of locking, this is a potential problem that you have to be aware of. But materialized views help with this, right? So materialized views handle all the locking and read before write stuff that you need to be aware of. And they also they specifically pair a base replica with a view replica in order to eliminate some of these failure scenarios that you have to be aware of when you're doing this manually. So in a lot of ways, materialized views they tend to be a lot safer than what you would typically write in your application. So in terms of what guarantees materialized views provide, the consistency level applies to both the base table and the view. The materialized view is always in the same key space as the base table right now. So if you are writing to a quorum of the base table replicas, you're guaranteed that a quorum of whatever the view replicas are have also gotten their updates. And this is what I was talking about earlier. It avoids this whole problem with multiple clients updating the views at the same time because there's partition level locking. If multiple clients write to a partition at the same time, one of them will hold the lock and it will do its view updates first. Then the second one, after the lock is released, can then read the new base table value so it knows what view record needs to be deleted. So it then deletes the first newly written view record and writes the correct final view record, if that makes sense. So this is a failure scenario you don't have to be concerned with. And in terms of repair, materialized views make repair a little bit more sane. So when you run a repair on the base table, every record that is out of sync on the base table gets replayed as a normal write. So it goes through the entire normal materialized view path whenever you do a repair. So when you repair the base table, the views get repaired as well. However, there are still a few limitations to exactly what repair can accomplish. I'll talk about those at the end of the talk here. Also, TTLs work as you would expect. If you TTL a record in the base table, when it expires, it'll also be removed from the view. Okay, so why not secondary indexes? Have any of y'all ever tried using secondary indexes in an application? No. Okay.
Long time ago.
Long time ago, yeah. And you only made the mistake once, right?
Yeah, everyone says not to use them.
Yeah. Everybody says not to use them. There are a few cases where they can work, but they're pretty limited. And the main reason is that Jonathan kind of touched on this, and I think there's a diagram here. The query pattern for secondary indexes, and essentially it needs to fan out to every node in the ring, because every node only indexes the data that it's already storing locally. This is a very expensive query, and especially if you only have, say, one row that matches your secondary index query, it needs to slowly query every token range in the ring until it gets to the one token range that has the row that you care about, and then it can return. So it's a very expensive, slow process. Whereas for materialized views, if you only have one row that matches, you query exactly a replica for that row directly. There's no extra network hops, no fan out, and it's a very efficient query. It's just like we always advise people to do with their normal data models. Yes.
So is there any advantage to the index where it doesn't replicate the data, actually just has just the index? You may have a little savings.
Yeah, in terms of say space efficiency, indexes are going to be much more space efficient, because all that indexes are doing is they're storing. It's a separate table, and the keys are index values. So say if you're indexing on age, there's a row for 23, row for 24, and then there's a partition for 23, partition for 24. Within that, there's a row that basically just holds the primary key for every base table row that matches. So it doesn't hold the full set of columns in the row, only the primary key. So that doesn't use a whole lot of space, but the downside is, on top of it being inefficient in this way, locally when you query the secondary index, it reads that index partition, and so it has a bunch of primary keys, but then it has to go and read each of those separately, which is also very expensive, right? Whereas with materialized views, you're looking at just reading one partition, a contiguous set of rows. So it gets you much closer to that optimal query pattern. And with materialized views, you're essentially duplicating the full row in most cases, or you're duplicating all of the data that you actually need to be able to read. If you add a materialized view on a table, you're roughly doubling the amount of storage, but in terms of query efficiency, it's going to be 1,000 times more efficient.
Has there been any analysis on standard industry patterns and what type of blow up you get?
For materialized views, or
Yeah.
well, they haven't been released yet, so
I just wondered if the core team went in and took some sampling of secondary indexes and standard patterns and when you need those.
yeah, no, we definitely got a lot of input from users, everybody that we've interacted with, all of our guys out in the field at DataStax that work with customers. Definitely a lot of input on this, but materialized views, what we essentially wanted to do is make it a lot easier for everybody to follow the best practice advice that we always give anyways. We always tell everybody to denormalize in this way. It's just kind of a pain to write all that code in your application for every single query you need to support. So materialized views just make doing the right thing a lot simpler, I think. So yeah, materialized views compared to how you're probably doing it in your application today is going to be the same amount of space usage. So just an example of creating materialized view. Jonathan kind of gave an example. Just looks like a select statement. You'll notice all the is not nulls there. Some of those don't have to exist. There was a recent ticket to make that not required whenever the column can be null in the base table anyways, like if it's in the partition key. But for everything else that could be null, you have to specify that it can include null columns in this case, because we don't want nulls in the primary key for the materialized view. And
yeah, so is there a pattern for, I mean, like with Oracle, you can tell it put the nulls at the beginning or at the end. Is there something that's done? I don't even know if the general Cassandra what's done.
Yeah, so we've talked about exactly how we want to handle that. So in general, Cassandra doesn't support nulls in the primary key right now.
Okay.
We're looking to change that, but since that hasn't been decided yet, we wanted to make this syntax mandatory so that it leaves us the option of how we want to deal with that later. So probably we will allow nulls for some of these. There are a few edge cases we have to iron out, but I don't know about specifying the sort order of nulls. That's a good point. I didn't realize that Oracle allowed you to do that.
Yeah, it's kind of just the end at the beginning.
Okay. I just assumed that nulls generally sort before everything else in most systems. So I think that's maybe what we're planning on, but yes. Has it actually ever been useful to sort nulls last?
I don't know, because I did mine first.
Okay. So, yeah, I mean, that's good to keep in mind. I'll keep that in mind. I thought I had a slide up here next. I did not. There's another slide somewhere, but this is a better time to talk about it. The where clause there, I was able to get in kind of at the last minute a more powerful where clause, so you can actually filter in the where clause on any of the primary key columns in the base table. So you can restrict it with all the normal operators, equality, inequality, an in list. So it allows you to do partial materialized views, which I definitely think is really handy. So there are a lot of use cases where that could be useful, but that you can only restrict on keys that are in the primary columns that are in the primary key of the base table right now, because otherwise there are some really tricky edge cases. Yeah.
So this is a creation of a view. Are you going to cover also like changing materialized views? Can you? Yeah,
you can change them. It looks the same essentially as changing a table in terms of like changing any of the options around compaction or compression or anything like that. You cannot, I do not think you can alter the columns that are in the materialized view after it's been created. You can
Wouldn't you just create another materialized view?
Yeah, you can do that. The main problem there is that you're going to use up all the extra space for the new materialized view that you're building while the old one still exists. So probably we'll look into adding more support for.
Yeah, but if you're changing it, that means you don't want the old one, so you add the new one and trash the old one.
Well, ideally you'd be able to change it without doing that,
So the use case I was thinking of is you said filters, and if you evolve your filter over time,
Yeah.
you had an end clause of X, Y, and Z. Now you want X, Y, Z, and ABC.
yeah,
You'd want to modify your materialized view to update the where clause.
Yeah.
That's something you can do.
that's definitely not supported right now.
That's what. Okay.
Yeah, yeah, that might be interesting to support. I'm not sure what problems that might potentially cause.
Well, you'd wonder about going back to the old data and refiltering and.
Right. Yeah, you have to potentially, backfill everything, rescan the table, and do a partial backfill or something, which might be kind of tricky. Yeah, if there was like a lot of interest in that or some really solid use cases, that's something we could potentially do. It's not supported at the moment though. And by the way, the materialized view doesn't, by default, it inherits all of the attributes of the regular table. So the compaction strategy and all that good stuff.
So it sounds like you can come make these after the fact. You could have a huge table, come create a materialized view, let it churn a little bit, and
Yeah.
it's caught up.
Yeah, exactly. It's kind of like the way that indexes build right now. So when you run the create statement, it just makes the schema change and then it starts populating it. In one of the system tables, there's a is built column that unfortunately right now you have to query every node to make sure that it's built everywhere. That's also something we're looking to improve, but that's the current state of it. And actually, the building process is more efficient than handling new records because it can skip the read before write because it knows that the records don't exist in the materialized view yet.
As in, like, having done this, you can go query that materialized view with whatever filter you want at that point.
Yeah.
To get just the stuff you're looking for.
Yeah, exactly. When you're querying the materialized view, you can use any of the things that you normally do when you're querying a table. Actually, the filter is on in the where clause for materialized views is a little bit more powerful than what you can normally use with select statements. It has like allow filtering turned on by default, and it allows you to do some types of filtering that you can't normally do. And the main reason is that all of those are equally efficient in terms of how the materialized view has to do them. So the efficiency of the query isn't really a concern like it is for normal select statements.
PDFs and stuff will still work on your materialized views.
So that's something that I definitely want to add support for soon, but it's not there yet. That's also in a later slide, but I don't like these slides. I might as well just like stop using them entirely. So UDFs definitely want to allow users to transform columns with UDFs, combine them or split them up into multiple columns. All that good stuff would be really useful. If I already know of use cases that would benefit from that. So that should come up soon. Yeah.
That's the end.
Do what?
Is that the end?
No, it's just my computer going to sleep.
Appropriate timing, wasn't it?
Yeah. Actually, I kind of like not having that on there. What was I going to say? Yeah, so UDFs are definitely going to be something that's added in here soon. Maybe at some point we'll look at doing aggregations as well, and that would allow you to. That's something that I also forgot to mention. Right now, the full primary key for the base table has to be included somewhere in the views primary key. And otherwise, you would have to essentially overwrite or merge multiple rows into one row in the view. And since we don't allow any sort of aggregation when doing that, the semantics would be kind of confusing, we think, for most people. As it is right now, you have to include the full primary key from the base table plus any other columns that you want. But you are free to rearrange the columns in the primary key however you'd like. So you can change the partition key, change the clustering order, all that stuff. Let me just make sure there's nothing else good in here.
Yeah, that's one thing, slides, whatever form, they're good reminders.
Yes, yeah. I'm after doing this talk, I'm completely sold. I'm like never going to use PowerPoint again, and I'm going to go back to.
What do you like?
So last time I did, I used a Wacom tablet and like drew out some of the slides before on like an infinite canvas, and then just like scrolled down it. It's kind of like having a giant infinite whiteboard that was already drawn on. It was way better. Yeah, so the performance characteristics, this is definitely a good one to talk about. So the main costs in writes on materialized views, there's two of them. There's the read before write, and then there's lock contention. So the locks are done per partition, per table. So if you have narrow partitions where you only have one row per partition, you don't really have to care about the lock because you're not going to be adding multiple rows to a partition. So for example, your primary key, if it's just like user ID, you don't have to worry about the locks.
Can you elaborate on the X and Y axis here?
Yeah, this is, yeah, those are terrible. Bottom one's probably time. Left one is writes per second. I have no idea what sort of number of clients
Time
writes.
does that like imply that you're just continue to stuff data in it and that's
Yeah.
what happens?
Yeah, exactly.
Time or volume of data on the bottom.
Yeah, it's time. This is a normal benchmarking system that we use for a lot of stuff in Cassandra. So lock contention, mostly you only need to care about that if you're doing a lot of updates to one partition at a time. The one that you need to be more aware of is the read before write. So this also doesn't affect narrow partitions very much, like if your primary key is only user ID, because if the row doesn't exist, Cassandra's Bloom filters are really efficient at telling you if a partition doesn't exist. There's only one row per partition. Knowing if the row exists is the same as knowing if the partition exists. So it can just essentially skip that read before write very quickly. On the other hand, if you have a partition with lots of rows in it, that Bloom filter check doesn't save you. You have to actually go look in the partition to see if the row exists. And it's also more expensive at that point to read one row out of a large partition. So as your partition starts to get wider, that read step becomes more expensive. And so you might see some degradation over time in write performance if you have a view on a table with wide partitions. So that's definitely one area where you may need to consider doing the manual denormalization, especially if in the application you already know if a row doesn't exist yet, or if you're doing an update, if the application already knows what the previous values were, so that you wouldn't need to do a read before write anyways, then you can get better efficiency by doing this manually. But if you don't need optimal efficiency and you care more about the safety and convenience of materialized views, then that's fine there. There are a couple of tickets to look at skipping the read before write, both at a view level. So saying that the view or the base table is append only, and you never do updates or deletes, it can always skip that read before write. And potentially we might do something at the statement level saying, I guarantee you that this row doesn't exist yet, or I know that the previous value of this column was X, right? So this would be like an assertion clause in an insert statement, something like that. Don't know if that API will end up there for sure or not, but it's something that might happen. Okay. Any other questions about write performance on views? Jason looks like
a question boiling there. Does it use the same batch mechanism underneath the covers?
Yeah. Actually, it does use the batch log. That's a good point. I needed to talk about that as well. It does use the batch log, but a little more of a restricted way. So initially there were 2 levels of batch logs for views. The first is at the coordinator, and then the second was at the base table replica. So the base table replica, yeah, it would, before it updated the view, or before it updates the view, it writes to its own batch log. It writes the view update to its own batch log. So this is essentially to guarantee that if that base table replica fails before applying the view updates, that those will get replayed at some point. And each of the base table replicas does that separately.
So it's a distributed batch.
Distributed batch log. Yeah,
That's cool.
exactly. We put in an option to take out the original coordinator level batch log. I think it either already got removed or it probably will be removed soon entirely. It didn't end up providing much benefit. So there is a little bit of overhead from the batch log, but I think that's generally quite minimal, especially because it's going to just go in the batch log mem table, and then as soon as the view write succeeds, that batch log entry is deleted, which that'll also go in the mem table. So ideally, you don't ever really see anything there hit disk, so that should be something that you don't have to care about too much. Let's see here. Yes, I should also mention the view updates are asynchronous by default. We've debated making them optionally synchronous, but for right now they're asynchronous. The one time where they do happen to be synchronous is where the base table replica is also the view replica. So if the partition key is the same, then it'll just update its view mem table synchronously when it applies the base table update. So if you have a use case where you really care about synchronous view updates, comment on the ticket that's named like synchronous view updates. All right.
So then the base table replica becomes the coordinator for writes to the view.
Yeah, so
Kind of.
So I mentioned really briefly earlier that each base table replica essentially pairs with a view replica. And whenever the partition key is the same, or whenever a base table replica can also be the view replica, it chooses to do that because it eliminates some failure scenarios, has performance benefits.
I guess I was wondering about hinted handoffs where that ended up. Hints would end up on the replicas of the rather than on the base coordinator.
So hints for the views.
View the views.
Yeah. Yeah, exactly. They would end up on the base table replica. That's correct. Yeah, there is a diagram about this, but it's like it's so bad.
Yeah. Yeah.
Yeah, this is so in this case, like these are the base table replicas, and these are the view replicas. So you can see in this case where they overlap, it just writes to itself, and otherwise it does the local batch log, and then writes. I already told you these are not my slides, so don't.
I'm sure they look better in Windows and PowerPoint.
Yeah, I'm sure. Yeah. I already mentioned all this, so let me make sure there's nothing else in here. Oh yeah, this is what I wanted to talk about. The some of the failure scenarios that you have to be aware of. So, and what the limitations of repair are. So basically what you can do right now is you can repair the base table, and if a node is out of sync, it gets streamed the changes from another node, and it kind of takes a special path, so it sends all of those through the normal write path so that the views can get updated. However, that can't handle cases where, say, if the view somehow has data that no longer corresponds to the base table, there's no way for a repair to detect that and to remove it. So you could potentially have stale data in a view. That would require essentially a bug in Cassandra. Hopefully it doesn't exist, but it's definitely a possibility. The other scenario that's problematic is, let's see here. I think it might be written down. No, it's not. Yeah, so if that's kind of similar to that first bullet point, is kind of what I was describing. This does not require a bug to happen, but if you lose all of the base table replicas for something, that view data can still exist, and there's no way of knowing that it's not supposed to exist anymore. Essentially, the problem is, if you have catastrophic loss of base table data, you don't also necessarily lose the view data. So it's kind of a problem, kind of not a problem as much, but I think at some point we will start writing some tools to do a somewhat expensive scan of the base table and the view to make sure that there's nothing extra in the views. It's just tough to make something efficient there. Yes?
Has there been any thinking about making materialized views that include data from multiple tables with compatible primary keys?
Not that I've heard of. Yeah, I'd be interested to talk to you about that afterwards if you have an idea for
Like that's
that'd
one of
be
the ways
useful.
that back in my Oracle days, that was one of the ways that it was cool to use views, is you could bring in data from different tables.
Do a join over multiple tables and
Even without
You
a
saved
join.
yourself a joy. That was the whole.
Yeah.
That was the driving reason.
With materialized views.
right.
Yeah.
I think in general it's not quite as valuable in Cassandra because just your data layouts don't normally benefit from that as much. But yeah, if you have something in mind that might be useful, I'd be interested to talk about that a little bit.
Yeah, the idea of join is a little strange.
Yeah.
You can still do it manually.
You can still what?
You can still do it manually.
Yeah, I mean,
The purpose of materialized view is to
automate the what you
automate
do manually. Right. Yeah. So whatever you could feasibly do manually, I guess you could do with materialized views as well. Okay. There was one other failure scenario that I wanted to talk about. Let me see if I can remember it real quick here. Can't remember. I think it was pretty far out there, so it's not too big of a deal. Okay. I think that's about it. You guys are starting to look a little bit tired as well, so.
Yet I have more questions.
Yeah, no, it's fine. Go for it.
In the first video we watched, you mentioned something about 200 rows per partition with an upper. I didn't understand what he was saying there. Like
He was talking about lock contention, the partition level locking for materialized views.
okay,
I'm not 100% sure what he was talking about. I think he was saying that if you have like 200 simultaneous updates to a partition, that's where lock contention starts to impact your throughput. I'm not sure if that's accurate or not.
because I thought he was talking about if you use materialized views with wide partitions, maybe is what he was talking about, like 200 rows per partition, and then it slows down the performance, the decrease.
Yeah,
Those lock
yeah.
contention. Yeah.
So I have a feeling he might have been slightly mistaken there, and really what you have to care about with the wide partitions more is that impact to the read before write performance. That's where you'll see more of that downward slope over time on throughput. Lock contention only matters about concurrent access to the partition, not the overall size, right? So. Anything else? Cool. All right. Thanks you guys for coming up.